If you have ever done a relaxed surface scan in ORCA trying to find some transition state or understanding the path of a reaction, you may have noticed that sometimes it takes a very long time. This is because in a relaxed surface scan you change a bond distance or a bond angle or a dihedral angle, and for each step in the scan you have to do a geometry optimization. If your molecule is small, then it can be quite fast, but if it's a big molecule, that can take a very long time. So in this video we're going to discuss some strategies to make this relaxed surface scan finish before we get old. So welcome to this ORCA tutorial. This would be video number 14. So what we are seeing here is a metallocorrole, a cobalt corrole with two apical pyridine ligands, and what I wanted to study is the dissociation kinetics of one of these pyridine ligands and possible replacement with water. So I'm going to do a relaxed surface scan on the cobalt nitrogen distance. So we can see here in the bottom left corner that the initial cobalt nitrogen distance is 2 angstrom, and I would like to scan it until 5 angstrom. So I'm going to move through the different trajectories of the relaxed surface scan that I performed, and you can see that it basically finished and crashed at a cobalt nitrogen distance of 2.1 angstrom. So this calculation basically crashed after some time, far before reaching the objective. And if we go to tools in Chemcraft, data summary, show energy graph from multiple XYZ file, we can see here that the initial energy is around 55 kilocal per mole above the minimum, and it takes a very long time and there are some jumps before we start to optimize. And there are a lot of small jumps because the geometrical convergence in the ORCA program was set too tight and it was not finding the correct minimum geometry before going to the next step. So this jump here probably happens on the second step of the relaxed surface scan when the distance was increased from 2 to 2.1 angstrom. So basically the calculation crashed probably because of some convergence problem. But the main problem is that it was taking too long, and that makes it more likely that it will crash by not being able to converge some geometry or self-consistent field. So here it is, the input file. We can see here that I'm using the keywords geom scan. B is for bond length, 0 is the number of the cobalt atom, 80 is the number of the nitrogen atom from the pyridine that I'm scanning, and I'm going from 2 to 5 angstrom in 31 steps. You have to put two ends. One end is for scan and the other end is for geom. This is what I wanted to do, but then in the geom field I also changed slightly the conversion settings. So here as comments we can see the defaults. For example, for energy change the default value is 5 times e to the minus 6, but I had increased these tolerances by multiplying them by a factor of 2. So I had 1 times e to the minus 5 instead of 5 times e to the minus 6, and the same for all the other parameters. So we have parameters for the root mean square gradient, for the max element of the gradient, and for the displacements. You have to fulfill a certain number of these tolerances in order to signal convergence of the geometry, which would allow you to go to the next step in the relaxed surface scan. So clearly for this system, these parameters were making the calculation go really slow. So these parameters are more than okay for many molecules, but in this case it was taking too long, which eventually caused it to crash. So the next thing I did is I did the same calculation. This is another file, but now I multiplied all these thresholds by 10. So now I have thresholds which are 20 times more relaxed or easier to achieve than the defaults. So for example, the energy tolerance is 0.1 millihartree when the default was 5 microhartree. And the same with everything. The root mean square of the gradient tolerance is 2 times e to the minus 3 when the default was 1 times e to the minus 4. So let's see what happens here. So this is the second attempt. And I'm going to again select the cobalt nitrogen distance, and you can see that it starts in 2 here at the bottom. And if I move the geometries, you can see that really fast the pyridine goes away, and I've reached a final distance of 5 angstrom. So if we go to tools, data summary, energy, we can see here that at the beginning we start from a certain energy, it goes down in around 8 steps, reaches a minimum, then makes a jump. That jump is probably on the first step of the relaxed surface scan. But after this, it goes like a saw, increasing and decreasing in one step. Each increase corresponds to a new relaxed surface scan distance, and within more or less 1 cycle or 2 cycles, it's converging the geometry for each step. So this allows me to scan really fast for the whole surface scan. And I can see more or less that the barrier from the minimum, which is around step 10, it's a relative energy of 0 kcal per mole, until I reach a certain distance. In here we are graphing the number of steps, not distance. We would have to retrieve that information from the trajectory file or from the output file at the end of the calculation. So basically the barrier is around 34 kilocal per mole. The maximum from this relaxed surface scan would be a good guess, perhaps, to start a geometry optimization of the transition state, an OptTS, or to use as an input for other types of calculations such as NEB, a natural elastic band, which is a very good method for finding transition states. This maximum here is most likely not a transition state. Maybe this one. It's not a transition state, but it may be close enough that we can start a geometry optimization of transition state from that structure. The problem with this is that the thresholds were maybe too lax, too easy to achieve. So that means that within 1 geometry optimization cycle for each step of the scan, it's converging. So maybe that's not so good. If you want to do a very rough analysis of the reaction surface, this may be good enough. But if you run the risk that you are not really reaching the correct structures because you have thresholds which are too relaxed. Now in this file, for another step of the reaction, I said, okay, this is not, the previous optimization was too fast, too few steps. What I did is change the geometry parameters, so I went back to a factor of 10. So all my thresholds are 10 times the defaults. 5 times e to the power of minus 5 versus 5 times e to the power of minus 6. 1 times e to the power of minus 3 versus the power of minus 4, etc. So this is half the thresholds that I had in the previous calculation. So now we are going to see what we got for this other step of the reaction. Now what I'm changing is another bond distance, is the bond distance between the cobalt and one of the water oxygens. So this is the oxygen from the water molecule that I'm going to scan. I chose this because it was the water molecule which was closest to the cobalt atom. So here the bond distance is 4 angstrom, and if I move the geometry optimization, we see that first the pyridine goes back in because clearly it was not far away enough, and then the water displaces the pyridine and gets to a final distance of 2 angstrom. If we go to data summary, we're going to see here that we have many more points. So we start a certain geometry, the energy goes down because it relaxes, and relaxation implies in this case that the pyridine rebinds to the cobalt, so it was not far away enough in order to not have a tendency to go back. But still, what we analyze in this step is basically the barrier for water displacing the pyridine. So we see here that there are many steps, and we get to a region around the maximum that has a lot of jumps. So we would have to redo probably a relaxed surface scan around the region that we are interested in order to get better values. But I have to be clear, this again is plotting all the steps. What we plot when we do a relaxed surface scan are the minimum values. If we take this region here, you would see that this jump corresponds to changing the step of the cobalt oxygen distance, and then there's a period of several relaxation cycles which at the beginning oscillate a little bit and then converge to a value, and when the geometry has converged, we shift the distance that we are scanning, which has been fixed throughout this optimization. So we see here that more or less we are taking around 6 to 8 or 10 cycles to converge. So this may be a good compromise if you have a large system. If we look at the minima and we plot, we could probably find a relatively good guess for a transition state optimization. If we go again, we can see this from the side, that the pyridine binds, and then the water slowly displaces the pyridine. So in this video we have seen 3 different levels of convergence criteria that may give a relaxed surface scan which takes too long and may crash in between, another relaxed surface scan which was too fast for my taste, and finally a relaxed surface scan that more or less has the number of steps that I find practical. Of course, this is not a general advice for all systems. You would have to test for your system what kind of conversion thresholds you want in order to have a reasonable result. But the main idea is that when you do calculations and when you're trying to understand reaction pathways, you have to try many different options and many different possible starting geometries and possible pathways. If each of these calculations, of which you have to do many, takes a very long time, that may be impractical. And I consider relaxed surface scans to be exploratory. They are the beginning of finding transition states. They are not the end. So I think it's better to have them finish in a reasonable time. So if you have found this video interesting, please like it. And if you find the other videos interesting or useful, please subscribe and share it to other people you may think could be interested in them. Thank you very much.